All right, so we are going to look at some of the basic probability rules today. So in general, probability starts with something called a sample space. And a sample space is the list of all possible outcomes. So anything that could possibly happen. So then specifically for probability, we'll be looking at events. So events can be one outcome, or a set of outcomes combined together. So all of the events together make up that sample space. So let's look at an example of a sample space and events by creating a probability model. All right, so what I want to think about here is if I am rolling one single die, so the probability will go in the second row here, and I want to know the probability of any given roll. So this is my sample space. When I roll a die, I can roll either a 1, 2, 3, 4, 5, or 6. That's it. That's all my possible outcomes. So down here, I would say the probability associated with each of these events. Well, I know the probability I roll a 1 is 1/6. Probability I roll a 2 is 1/6, and so on. So here, they all happen to be the same. So this is not something that will always happen. They, of course, won't all always be the same, but when I'm talking about rolling a die, as long as it's fair, they all have an equal chance. Okay, so some possible events we could create for rolling a die. So a lot of times we give our events capital letters. So we're going to say, let event A equal rolling a 3. And we're going to say event B is rolling an even number. And event C is rolling a number greater than 4. Okay, so these are just the ones I picked. You could really pick anything associated with rolling a die. All right, so we want to find the probability of each of these events then. So here is how we're going to write this. So I'm going to say the probability of event A. So this is pronounced the probability of A. Okay, so if event A is rolling a 3, what's the probability that on one single roll I get a 3? Well, it's 1 out of 6 options, so it's going to be 1/6. All right, the probability of event B. So B is rolling a number greater than 4. So my options for numbers that are greater than 4 would be a 5 or a 6, right? Greater than 4 is only 5 and 6. So from here, I have 2 outcomes that are greater than 4 out of my sample space, which has 6 equally likely things, or 1/3. Oops, that was for C. Sorry. I'll just change it. So I was looking at a number greater than 4, so that would be C. All right, now let's find the event B. So B is rolling an even number. So I would look at my sample space. Of my 6 equally likely outcomes, I have 3 even numbers, 2, 4, and 6. So I would have 3 out of 6, or 1/2. Okay, so we're going to go through kind of some of the more basic probability vocab words. So looking at a complement. So things that complement each other are things that go together. So the complement of event A is not A, where A does not occur. Okay, so you want to think about this as like if event A is it's going to snow, the complement would be that it's not going to snow. All right, and since they're exact opposites of each other, we can find the probability of the complement of A if we know the probability of A and vice versa. So the notation we use here is A with just a superscript C to stand for complement. All right, and the probability of A is equal to 1 minus the probability of A complement, since they are opposites of each other. So if there's a 70% chance that it's going to snow, there would have to be a 30% chance that it's not going to snow. That's all that's saying, is that the two things together have to add up to be 1. Okay, our next kind of vocab word here is mutually exclusive. Mutually exclusive, another word for that is disjoint. They mean the exact same thing. Okay, so two events are mutually exclusive if they have no outcomes in common. In other words, they cannot occur at the same time. Okay, so if we have two events A and B that are mutually exclusive, we say that the probability of A and B is equal to 0. This is saying there is 0 chance that they are both going to happen. All right, so let's look at an example. So when we're thinking about rolling a die, like that probability model we were looking at, if I say A is rolling a 2 and B is rolling an odd number, there's no way that both of those things could happen at the same time. Right? So I cannot roll both a 2 and an odd number because they are mutually exclusive. So if we have two events that are mutually exclusive or disjoint, we say that the probability of A or B happening is just the sum of each of their individual probabilities. So the probability of rolling a 2 or an odd number in this example, so the probability of rolling a 2 is 1/6, plus the probability of rolling an odd number, there are 3 odd numbers out of 6. So overall we get 4/6 or 2/3. So that's the probability I get a 2 or an odd number. All right, so at this point you should pause the video, go ahead and try these 3 problems on page 309, and then come back and see how you did. So go ahead and pause, try the problems, and come back. All right, so let's see how we did here. So 309 was talking about, or the problems on page 309 were talking about choosing an adult at random, and we're given information about cholesterol levels. So first they wanted to know why A and B are mutually exclusive. So why can they not occur at the same time? So I have a person cannot have a cholesterol level of both 240 or more and between 200 and 239. So a number cannot fall in both of those ranges, so they would be mutually exclusive. Number 2 was talking about what does A or B mean. So this means a person either has a cholesterol level 240 or above, or they have a cholesterol level of 200, between 200 and 239. So it's in either one of those categories, but cannot be in both because they are mutually exclusive. All right, then in part 3, they gave us a new event, C, which is saying a person has normal cholesterol, which is below 200. So we wanted to know the probability of C. So we actually need this last part of number 2 there. So the probability of A or B. So because they were mutually exclusive, we were using this formula from the last page here. So I added the probability of A plus the probability of B to get 0.45. And now we can look at number 3. So the event C, a person has normal cholesterol or below 200. So that would be the complement of this event we talked about right here. Because this represents above 240, 200 to 239, I want to know everything else. So below 200 is the complement. So event C is going to be 1 minus 0.45 because that would make up everything in the sample space. So below 200, 200 to 239, and above 240, those would be all possible outcomes for cholesterol. So they all have to add up to be 1 because that represents everything in the sample space. All right, so just a few more vocab words here. Okay, so we've been talking about the idea of or. So that is specifically called a union in probability. So the union of two events is where A or B or both happen. And the notation we use for this is just a big U between the two. So if we're talking about probability, we would say the probability of A union B. Something like that is what we would write. Okay, along with the union, we have something called an intersection. So intersection is where two things collide. So an intersection is A and B, and that's where A and B both happen. So the symbol for an intersection is just an upside down U. So it's A, this would be read A and B. All right, and we need both of these things to look at something called the general addition rule. So the general addition rule is what we need when we're finding the probability of a union for two events. Okay, so we say the probability of A or B is equal to the probability of A plus the probability of B. Okay, so when we had disjoint events, we had the same formula started. But when our events are not disjoint, we have to subtract off the intersection. So it's probability of A plus probability of B minus the intersection. And the reason for that is this here. So we have to subtract off the intersection so we don't count the both events twice. So I know the union means A or B or both. So this is going to be everything that's A. This is going to be everything that's B. Now those events that are both A and B are included here and here. So we're actually counting them twice. So we're going to subtract off the things that are A and B once, so then they are only counted once. All right, next you should be pausing here and trying numbers 2 and 3 on page 311. So give them a try and then come back and see how you did. All right, so number 2 gives us two events, face card and a heart card. All right, and we wanted to know the probability of face and heart. So face and heart. So how many cards out of the deck are both a face and a heart card? There are 3 of them. So we have the king, queen, and jack of hearts. So 3 cards out of the entire deck, which is 52. So that, when we divide, we get 0.058 for our probability. So for the and, you're just counting how many events would be in that intersection, dividing by the total sample space. All right, 3 then is saying, why is the probability of F or H not just equal to the probability of F plus the probability of H? And the reason for that is that these are not mutually exclusive. So we have some cards that are both a heart and a face, so we cannot simply just add the probabilities of F and H. So what we need here is the general addition rule. So the general addition rule, I would be finding the probability of F, so face cards. There are 12 face cards in a deck out of 52, plus the probability of H. So there are 13 hearts out of 52, and this is where I'm subtracting the intersection. So all I'm doing, guys, is following this formula right here that was on the last slide. All right, so when I do this, those 3 cards, the king, queen, and jack of hearts, were counted here as face cards. They were also counted here as hearts, so I'm going to subtract them off once, so they're only counted once, which gives us 22 out of 52, or a probability of 0.423 of getting a face or a heart or